Today, let's solve a problem graph valid tree. So this is another LeetCode premium problem. So we are going to be solving it on LintCode because it's free on that website. So we are going to be leveraging that. And also this is another problem from the blind 75 list. So this is graph valid tree. So we are going to be filling in one more problem from that blind 75 list today. So this is a graph problem. We are given n input nodes labeled from 0 to n minus 1. And we're given a list of undirected edges. The undirected means that the edges will go both ways. So, we have a couple nodes like this, so the edge could go in either direction. And we just want to write a function to check whether these edges and nodes create a valid tree or not. So we know it's going to be some kind of graph, right? The graph could look something like this. Right, we don't care too much about the values here, but let's say this was the shape of a graph. Does this count as a tree? Well, yeah, this is a pretty familiar looking tree, right? So we would say, yes, this is a tree. But if I add one more edge like this one, is this a tree? It's not a tree, and the reason being is because we have a loop inside of this graph. Trees are not allowed to have loops. That's just something that you just have to kind of know the definition of, because in this problem they don't tell you what exactly is the definition of a valid tree. So we know trees can't have loops. And there's one more condition for it to be a tree. A tree needs to be connected. So for example, if I had a graph that looks like this is not a tree because every node is not connected, right? Like this node over here is just by itself. It's not connected with the rest of the nodes. So for it to be a valid tree, we can't have loops and every node needs to be connected. So simply we can take our input nodes and our edges and then check, are they connected and do they not have a loop? And to be able to do that, so you can see the format that we're given our edges in, but we want to using these edges, create an adjacency list. So basically for each node, for example, 1, we want to know what neighbors does 1 have. In this example, 1 only has a single neighbor, right? And that's 0. What neighbors does 2 have? In this case, 2 has a single neighbor and it's 0. That's basically what we want to do. We want to create a list of neighbors for every single input node. And once we get that, it'll be easy to traverse the graph and then we can perform our check to make sure that it is a tree. So let's say we were given a graph like this. Is this a valid tree? Well, just by looking at it, we can tell yes that it is. But what kind of algorithm can we do to determine that? Well, let's start at any node in this graph. We're always just going to choose node 0 because it's, the smallest value. Every single graph is going to have at least a node 0. If we don't even have node 0, like if the number of nodes, if we don't have any nodes at all, then we can return true. Basically, an empty graph does count as a tree technically. But so in this case, we don't have an empty graph, so we're going to start at node 0. What are we going to check? Basically, we're going to do a standard graph traversal. You could do breadth first search, but I'm going to do depth first search. And so for every single node, we're basically going to go on and visit its neighbors recursively and then continue to do that until we visited every single node that's connected to the 0 node. At the end, what we're going to do is take the number of input nodes that we were given, in this case it's 5, and then we're going to check if the number of visited nodes matches. If the number of visited nodes matches the input value for nodes, that means that every node inside the graph is connected, right? That's one of the things we're looking for, is the graph connected? If the number of nodes we visit matches the number of nodes given to us, we can guarantee that the graph is connected. The other thing we're going to check for is to make sure that this graph does not contain any cycles or loops. If we ever encounter a cycle, like for example, we have an edge like this, if we went here, we went here, we went here, and then we got back to 0, that counts as a cycle, then we would have to return false immediately. But if we don't reach a cycle and this condition ends up being true, then we're going to return true. So since we start at 0, what we're going to do is to our set of visited nodes, it's going to be a hash set because that's the most efficient way to do it. So we're going to add that node 0 because 0 has been visited. So then we're going to recursively go to its first neighbor, 1. So now we're going to be at 1, right? And from the perspective of 0, we're going to visit 1. After we're done with that, we're going to visit 2, then we're going to visit 3. But first, we're going to start at 1. So now we're at 1, right? We're going to go ahead and add 1 to the visit set. And we notice 1 has 2 neighbors, right? It has a neighbor 0, and it also has a neighbor 4. Now, one problem with our algorithm is for every node, including 1, we're always going to want to visit every single neighbor it has. We know that the neighbor 0 has already been visited, right? So if we end up going back here, we're going to see, okay, we're visiting 0 again. 0 happens to be in our visit set, so that means we detected a loop. But technically, this graph does not have a loop. So how can we get around this edge case of every time we visit a node like 1, we're going to end up going back to where we came from, and that's always going to give us a false positive of detecting a loop. It's going to be a false positive for a loop. How can we get rid of that? Well, every time we visit a node such as 1, what we're going to give it is one additional value, and that's going to be previous. Previous is going to be what the previous node we just visited was. So when we get to 1, we're going to say the previous node that we visited was 0, so we're not going to go back to 0 from this position. If there happened to be another way back to 0, for example, let's say 4 ended up connecting to 0, then we would detect a loop, right? But if we ever got to 4, we would say, okay, the previous value from 4 happened to be 1, right? So this 4 came from 1. So we won't get any false positives if we do it like this. So from 1, the only node we're going to visit is going to be the neighbor 4. So yes, we're going to go to 4 now, and we're going to see, okay, is 4 already visited? It's not, so let's add it to the visit set. So 4 is going to be added as a node that's been visited. Now, we know the previous node from 4 happened to be 1, right? So we're never going to go back directly to 1. We're going to skip that, and we're going to check, does 4 have any other neighbors? It does not, so this is going to be our base case for our depth first search. We're going to return true because so far we have not encountered a loop. So we can return true. If we did encounter a loop, then we would have to return false. But so far we're good. We're going to return, and then we're going to get to 1. And from 1, we have no more neighbors left to visit either, so then we're going to return back to 0. And by the way, what kind of previous value would we feed into 0? Because it's going to be the first value it's going to be the first node that we end up visiting. So we can give it a default previous value of -1 because we know that no nodes in the graph are actually going to have a value of -1 because they start at 0. So now let's go to the next neighbor of 0. We'll go down to 2. Okay, check. Has 2 been visited? It hasn't, so let's add it to our visit set. 2 is being added. Now 2 does not have any additional neighbors. It only has that neighbor that it came from, node 0, so we're not going to keep going. And then we're going to go to the last neighbor of 0. We're going to go down to 3, and once again, check, has 3 been visited? It hasn't, so then we're going to add 3 to the visit set. Then we're going to go back to 0, and then 0 does not have any additional neighbors, so now we're done. We didn't detect a loop, so that's good. But let's make sure that the graph is connected. So the number of input nodes are connected, and it happens to exactly be 5, right? So in this case, we are going to end up returning, right? So therefore, in this case, we would have to return length of our set would have been 4, but the n value was 5. So does n equal 4, the size of our visit set? No, that does not match, right? So therefore, in this case, we would have to return false. We didn't detect a loop. What we have done is because it's false. We didn't detect a loop, but the graph is not connected, so we have to return false because it's not a valid tree. And similarly, let's say we had an additional node from 4 to 0, then in our depth first search, what we would have done is, okay, we'd have gone to 0, and then we're visiting 0, so we'd check, is 0 already in our visit set? Yes, it is. 0 is right here, so that means we're visiting it twice, that means we detected a loop, that means we return false immediately. So that's the main idea of this algorithm. Now the time complexity, since we're only having to traverse each node once, at most once, and each edge at most once, the overall time complexity is going to be number of edges plus the number of vertices or nodes, so just E plus V. And that's also going to basically be the memory complexity as well, because we're going to be doing this recursively. And we're also going to be needing to create an adjacent to get into it. So one base case is if we aren't given any nodes at all, so if n was 0, so in that case we would return true. There's no graph to traverse, but an empty graph does technically count as a tree. And if we do have some nodes, then we're going to create an adjacency list. So what I'm going to do is, first of all, for every single node in our input, so basically n is the number of nodes, so for I in range n, I'm going to create a pair in our hash map, and each pair is going to be the value of that node and an empty list initially. And then I'm going to go through every pair of nodes in every single edge. So an edge is basically a pair of nodes being connected, right? So what I'm going to say is, and remember these edges are not directed, so they go both ways. So for the adjacency list of n1, I'm going to append n2 to that list, and similarly for the adjacency list of n2, I'm going to append n1. And then I'm going to start defining our depth first search. Remember, we are going to have to know which node we're visiting, so I'm going to use I as the value of the node that we're visiting. Remember, we're also passing in one other variable, the previous node that we came from, so we don't get false positives for loop detection. And so you can see I'm defining this function inside of our outer function. That just means I don't have to pass in the variables like adjacency list into this each time. And actually, I need to define one more variable. That's going to be visit, which is going to be a set, which is going to keep track of all the nodes we've visited. So one base case is going to be if I hey, basically a pair of nodes being connected, right? So what I'm going to say is, and remember these edges are not directed, so they go both ways. So for the adjacency list of n1, I'm going to append n2 to that list, and similarly for the adjacency list of n2, I'm going to append n1. And then I'm going to start defining our depth first search. Remember, we are going to have to know which node we're visiting, so I'm going to use I as the value of the node that we're visiting. Remember, we're also passing in one other variable, the previous node that we came from, so we don't get false positives for loop detection. And so you can see I'm defining this function inside of our outer function. That just means I don't have to pass in the variables like adjacency list into this each time. And actually, I need to define one more variable. That's going to be visit, which is going to be a set, which is going to keep track of all the nodes we've visited. So one base case is going to be if I is in the visit set, that means it's already been visited. That means we've detected a loop. That means we can return false. If not, that means I hasn't been visited, so then we can go ahead and add it to visit. So let's add I, and then let's go through every single neighbor of I. So every single node, let's call it J in the adjacency list, so the list of neighbors of I. And if J happens to be equal to the previous node, the node that we came from, then we're going to skip this iteration of the loop. We can do that with the continue statement. If it's not the previous node that we came from, then we're going to call depth first search on this node, j, and as the previous value, we're going to pass in I, because that's where we're coming from when we arrive at node j. Now, if the return value of this is equal to false, so if not the result of this, then we're going to immediately return false, because that means we detected a loop. If this does not return false, then we're basically going to continue. We're going to go through all the other neighbors of the node I. And if we go through every single neighbor without returning false, then we can return true, meaning we did not detect a loop. So we want to now return the result, right? And of course, we know we're going to have to call our depth first search function. We're going to start at node 0, and as the previous value, we're going to pass in -1, because -1 is never going to exist in our graph. But is this enough? Remember, our depth first search, what it's returning as the true and false is only detecting if there's a loop, like a cycle, or not. But it's not making sure that the entire graph is connected. So we're only going to return true if this function returns true and if n, which is the input of the number of nodes, exactly matches the length of the visit set. Basically, every single node happened to be visited. That means every node is connected. That means the graph is a tree. So only if both of these are true are we going to return true. So this is the entire code, and I can show you, if I slide this up a little bit, that this does run, and it does run pretty efficiently. So I hope that this was helpful. We're basically just doing a standard depth first search on this graph. And if this was helpful, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. Okay, detected a loop. If this does not, function returns true. Okay, list, so the list of neighbors of I. Let's get into it. So one base case is if we aren't given any nodes at all. So if n was 0, so in that case we would return true. There's no graph to traverse, but an empty graph does technically count as a tree. And if we do have